part when dealing with series is dealing with this dot, dot, dot. Because you could have potentially a huge number of terms here. And what we did last week was we looked at a way of finding what we call a closed formula for the sum of an arithmetic series. So we found a way to eliminate the dot, dot, dot so that you could just give it the first term and the last term, and you could compute what this series was directly. And the whole trick here is we need to figure out some way of not having a variable number of terms. As n goes up in our sum, we're adding more and more terms because n literally tells me how many terms we have. So the trick that we used for arithmetic series was we noticed that if we write the same sum backwards like this, what's this, 29? Wait, how much am I going up by here? Yeah, 29. Like this. And then you add them together. Instead of we still have all the terms, but it still lets us simplify them because all the terms end up being the same thing. They all end up being 34. And so you don't actually have to write them with a dot, dot, dot. You can write 34 times however many you have, and now you're off to the races. So what can we do for a geometric series? In a geometric series, every single term is the way you get from one term to the next is by multiplying by a constant instead of by adding by a constant. So here, my first term is 3, but then I multiply by 2 to get 6, multiply by 2 to get 12, and so on. You could double check to see if the same trick works. We say hopefully. But if you kind of check with a small series yourself, you'll see that it's just not true that writing it backwards and summing all the terms, you'll get the same constants. So we need a new trick. And here's what that trick looks like. Let's start again by writing the same series. Only now we're going to try and shift the series, so to speak. So I want this term to become 6, and this term to become 12, and this term to become 24. And the reason why is because we're going to subtract one from the other in a second. And if we can shift each of these terms up, then that will mean that a whole lot of them cancel with each other. So let's see, how would we shift it up? Well, I guess to turn 3 into 6, we multiply by 2, and to turn 6 into 12, we multiply by 2, and to turn 12 into 24, we multiply by 2. So if 2 is the constant growth factor, we're always multiplying by 2 to get from one term to the next. If I just multiply both sides of the equation here by 2, it's going to look like this. 2 times the left-hand side is going to be 2 times the entire right-hand side. Let's sort of expand this out to see what it looks like. Well, we know what it looks like. It's going to shift each term up to the right. So 2 times 3 is going to give us 6. And then 2 times 6 is going to give us 12. And 2 times 12 is going to give us 24. And we're going to go all the way to the end so that we'll have 2 times 1536 is going to give us, let's check, 3072, it turns out. So we'll have an additional 3072. Whoops, 3072 on the outside there. Great. So we've done it. So now we can subtract and look what happens. There's nothing to cancel with 3, so that goes over. And there's nothing to cancel with 3072, so that moves down. But 6 cancels with 6, 12 cancels with 12. So because we started with our series and then we took every term and we sort of shifted it up by 1, all of the terms cancel here except the first term, and then we have an extra term at the end. So if we write this out, we've got 2s equals 3, and then remember, we're subtracting the bottom one. Oh, wait, hold on. So if we're subtracting the bottom one from the top one, we actually have s minus 2s, because we have this one minus that one. Then we've got 3, and then we've got, there's nothing over here, so whatever, nothing minus 3072. And now if we're trying to solve for s, we can factor an s out of both sides here. So that means 1 minus 2. And I'm keeping all of these numbers unsimplified right now because we're not actually looking for a numerical solution. I'm going to try and generalize this pattern in just a second because instead of doing the same steps every time with numbers, we want to find a general pattern. So if I'm going to divide through by 1 minus 2, now I get this. And you could figure out what that was. So let's go back over here and now run through that same process, but imagining a sort of a general geometric series. So in a general geometric series, we're going to start with some initial term. We could call that A1. And then to get to the next term, we multiply it by some constant growth factor. So I'll call that A1 times G. And then to get from here to the next one, I'll multiply it again. A1 times G is this one, times G again will give me G squared, and so on. And if I have n terms, okay, so here's a confusing thing. If I have n terms, I don't write G to the n, because think about what our terms are numbered here. This is term number 1. So if my nth term was a sub 1 times G to the n, that would imply that my first term should be a1 G to the 1, but it's not. So it's sort of like we're starting with G to the 0 here in the first term, and in the second term we have G to the first, and in the third term we have G squared. So the number of G's we've multiplied by is always one smaller than our term number, because in term number 1 we don't have any G's to start with. It's like we only multiply by a G when we go to the second term and then the third. So this should actually be n minus 1 is going to be the nth term in the series. Okay, so let's do the same process. See if you can remember for a second. If your friend said, I don't remember how to do the geometric series, what would you tell them? We start by writing the series again, but then what's the trick that's going to let us cancel things? See if you can say it. Saying out loud is learning. See if you can say it out loud. What do you do that will let us cancel? Okay, I hope that what you said is you multiply both sides by whatever the growth factor is, because we want to shift this term to be the second term and the second term to be the third term and so on. So if I multiply by G on both sides, here, let me rewrite it actually. Well, no, we can just write it this way. So I'm going to multiply by G on the left here. This is going to be A1G. This is going to be G squared. This is going to be G cubed, and so on. And then here at the end, if I multiply A1 G to the n minus 1 by another G, it's like I'd add the two exponents, and so now that's one more G. So I'd have G to the nth power. All right, so now I can do my subtraction. Scoot it over a little bit. So I've got S minus GS. Remember, S is my sum, G is my growth factor. And I haven't written it in a nice shifted way, but you can see A1G is here, and I'm subtracting another A1G here. So this cancels with this cancels with this. The one that I didn't write inside the dot, dot, dot cancels with this one. And it's going to cancel all down the line. This one's going to cancel with the one right before this one. So just like last time, I've got my first term here has nothing. There's nothing that's going to subtract to cancel it. And then I have an extra last term here, corresponds to this one over there. So I'll have A1 minus A1G to the n. Let's factor the S out of both sides here. So I'll have S times 1 minus G. A1 minus A1G to the n. And now let's divide. So I have sum equals A1 minus A1G to the n over 1 minus G. So that's the process. Like we did before, it's nice to give some meaning to this. So A1, that was our first term. Is A1G to the n the last term in our series? No, it seems like it's not, because the last term in our series was this. It was A1G to the n minus 1. But if I was going to write one more term in the series, the term after this one would be A1G to the n. So a nice way of thinking about it is we've got that the sum equals the first term minus the term after the last term. So like the next one after the last term, divided by 1 minus your growth factor. I haven't thought yet, actually, whether or not there's a nice geometric interpretation for this, like we did for the arithmetic series. It might be worthwhile thinking about it. Often there is. I'm not sure about this one. Anyway, there we have it. Come back in the next video and we'll try and use this formula for a couple of problems.